Welcome to the second episode of the Coordinate podcast. I'm your host, Shabik Dev. AI is making intelligence digital, crypto is making institutions digital, and the digital intelligence needs digital institutions. The mission of this show is simple: talk to the most fascinating entrepreneurs and intellectuals shaping this future and extract lessons that you can actually apply. In the last episode with Karthik Nayak, we explored consensus from a theoretical standpoint. Today, we are getting much more concrete by talking about what real high-performance implementations actually look like. Most blockchain infrastructure today is built as a monolith, one stack, one set of trade-offs designed to be good enough for everyone. But that balance comes at a cost, especially if you care about very specific application guarantees. Today's episode is about the opposite idea, specialization. What happens if you decompose the blockchain stack into core primitives and deliberately optimize them independently? To explore that, I'm joined by Patrick O'Grady, the founder of Commonware, and Brendan Chou, a core engineer at Commonware. Together, they are pushing an anti-framework philosophy aimed at building purpose-built on-chain system. Patrick, Brendan, welcome to the show.
Yeah, thanks for having us. I think you may have given a better introduction than I could have. So, excited to be here and talk about Commonware and talk about some of the work we've been doing on consensus.
Yeah. Likewise, yeah.
Awesome. I want to start by reading a short line, Patrick, that you wrote in one of the blog posts about collaboration at Tempo, and I believe that this short paragraph, it actually captures the thesis of what you are building the best. So let me read this. So, quote unquote, I started Commonware because I believe the best on-chain experiences will develop a sustainable edge through specialization. One size fits all frameworks prioritize balance across application, but they prevent ambitious teams from pushing the edge. Commonware instead provides standalone primitives across networking, storage, and consensus that engineers can remix as they see fit. So Patrick, this line reads like a rejection of the default way blockchains are built. So I'm curious, what broke you?
And a run-on sentence there. Yeah, but I think so I mean, to back up a little bit, so previous to Commonware, I was at Avalanche for like 3.5 years, and then before that was at Coinbase for like 2 years, and for a long time have been working on really getting deep into this whole idea around how you actually abstract interactions with blockchain. So at Coinbase, I worked on a project called Rosetta, now Mesh, which if you've used it or not used it, you may have strong feelings because I think it was one of my first works, so don't hold it against me. I think there were good parts and bad parts. From the beginning was like thinking around like the abstraction of how do we input and output data from blockchains, and then through that going deeper into okay, now people are using these execution models, and on top of that sits on top of consensus, and ultimately when I started Commonware, it was driven by motivation because in talking to a lot of the great teams, no one was asking for like more frameworks or like easier to use setup. It was, hey, I'm maintaining this fork of a fork of a fork because I've changed like all these different things, and I'm afraid to touch anything because I don't know what's going to happen. Like there's so many layers of abstractions I'm violating or breaking to get what I needed to do that it just creates this stasis where now applications can't really do anything. So it's easy to get started, and then you don't know how like tough of a corner you've backed yourself into. And so through that, like in starting Commonware, I was really motivated and interested in this idea that maybe we are abstracting things wrong. Now that's not to say like like kind of this sort of OS model of architecting blockchains or frameworks doesn't work for some things. Like it's great for like a shared execution layer, let's say, where you have to regulate access to certain parts of state and you want to like abstract the resource in some sort of gas metering. But when it actually comes to developing the stack, I don't think it needs to extend in the same way. And so I think if you look back at this is a very abbreviated history, but like Bitcoin, very specific in what it was trying to do. Everything was tuned for Bitcoin and what Bitcoin does around payments. Now you can say that was tuned well or not, but it was tuned for that. Then the idea was like, we want more Bitcoins. So how can we like save energy by like not having to build like our own Bitcoin like stack each time? So like let's abstract it like we did with everything over the last 30 years that runs embedded, which is OS model. Like we'll have some general abstraction and then people will integrate that general abstraction And just like with operating systems, right? Like it'll get fast enough that it won't be a problem for most applications. So like you don't have an Excel laptop, you have like a Mac. And that worked for OS, and it worked for a while for crypto, but over the last few years, I think we've started to see it break a bit and really be more of a hindrance than a help for people doing really crazy stuff. And so the idea was to say, well, what if we didn't actually impose any sort of logical hierarchy of the components and instead just gave the people what they want? You want P2P, you want consensus, you want storage, you want this. Just import it however you want to. We don't care. There's just one line of traits you can kind of use however you want. And it turns out, and the theory was that great teams would prefer that over like this really easy to spin up kind of abstraction. So so if you look at it, it's designed very differently than any other blockchain framework you've probably used before. And we're not optimizing for, can I spin this up in a day? We're optimizing for, can I maintain this for 5 years and actually like twist the knobs I need to drive what we think is really interesting and differentiated performance to your application. So downside, takes about 30 minutes to explain to anybody that's asking what Commonware does for the first time. But our model is to work with a handful of really great teams and then make sure that what we do makes sense for them.
I'm curious, given that you mentioned that it's all about breaking the abstractions into some small primitives. Yep. It might be worthwhile to go deeper. What are all these primitives are there? Like, is it just P2P? Is it just consensus, or is it more than that? Because that's what, like, if you talk with people think, oh, it's just maybe P2P, there is consensus, and maybe nothing else.
I think today we have something like over 40 primitives and like primitive dialects, we call them. So there are probably 6 or 7 top level primitive types, and then within those, like usually 3 to 4 different variants. And so the idea is that we break things apart. I think the core ones right now, we have our runtime, P2P, consensus, storage, parallel, cryptography, coding, broadcast. And basically what they do is when you're building a blockchain from scratch, we should have a primitive, we think right now, for almost every piece that you want to build. So if you have a network, you probably want a P2P. Now, on top of P2P, you probably want to run consensus. Consensus probably needs cryptography. On top of that, you probably have some execution environment that needs storage. And you can then take what we have as these like standalone components and then inject your own logic at each point. So it looks a lot more like you're building and like importing a stack rather than fill in this like one sector where your application goes and we'll handle everything. So what that means is like if you've never built a blockchain before or like integrated at a deep level, probably don't start with Commonware. In fact, I would almost recommend you don't start with Commonware because you'll have to do a lot of thinking to kind of. We have a lot of examples, but it's definitely more catered at this point to like what I would call the pro mode kind of developer, where like you know what you want and you just want us to get out of the way. Yeah.
I think in this case, basically, you have tried using existing monolithic stacks, and you, while attempting to use them, you didn't find them fitting your solution. So you come here, take these components, mix them up, because now you know what you want, and you can just mix and match them and just build the thing.
I would say almost all of the people building with Commonware I've at least talked to have come from somewhere. No one's like, I'm building for the first time with Commonware. It's like, I've been here for 5 years and like, I fucking hated it. Like, I'll do anything differently if I can. And that's usually the common story. And I mean, when I was originally kind of validating this idea, the kernel I really, no pun intended, the kernel I really hung on to was, if you talk to anyone that's been working in the space for a while that is using one of these frameworks, whatever it might be, and you ask them, like, do you like it? Like real applications. I would say the best I always heard was meh, and much often heard much worse. And that's not to say that it like they didn't do what they meant to do. Like they shortened the time to launch blockchains. Like they abstracted away a bunch of the details that you would have to think about, which probably for like standard applications at low throughput are probably inconsequential. But if you want to now, if it's now like a blockchain's a dime a dozen, you know, and you want to win, you can't just like launch another standardly constructed thing. It's like, all right, what is this application trying to do? How am I going to introduce novel ways to make it better and build that advantage? And so if you come at it from that perspective, you really don't want a framework. You just want to basically take pieces off the shelf that are already commoditized and then just focus on the parts you want to do. And so if you look at the Tempo code base, for example, you brought up, they do this very well. So like they basically, all the parts that they don't feel is their edge, they take a Commonware piece off. And then all the parts that they think are really special to Tempo and like what they're doing, which are great, we have no insight into it, like they're doing amazing work that's unrelated to us. They focus on that and they just hook up the pieces. And that's exactly what we had in mind with Commonware.
You mentioned that there are like 40 such pieces almost, and maybe it's worth going a little bit deeper on like what are top 5 pieces. I was going through your website. It's like there is a runtime, there is some P2P broadcast, there is some reshare or something like that, which seems very critical, all those things.
Yeah. Yes, I mean, we try to give, I think like a lot of the product side of this is like where to give the knobs to turn. Like we could make every possible piece generic, and like when you configured it, we already run afoul of this a little bit, but like have like 50 different generics you have to configure. You know, we try to balance it to like a reasonable level of customization of the pieces we have. But yeah, the top primitive that people know us for, I'd say these days, is simplex. We have our own simplex implementation with a number of tweaks to it that make it really interesting for some applications, and it's very optimized. So we do, for example, buffered signatures, so we can really minimize the overhead of consensus, particularly the expensive parts with like signature verification. That's our number one primitive. Like when people come to us, I think almost every instance has simplex in it today. The other thing that we're known for is this runtime. So everything that in Commonware is deterministically runnable, so like simulated. So you can locally reproduce like the entire run on your computer. So if you, in your test environment, what that means is like you have a seed, this thing controls everything. So like randomness, clock, task execution order. And so if you have a unit test that fails, you can just rerun it and get exactly the same error again. And so
hold on, this seems fascinating. So does this include peer-to-peer networks across like multiple nodes?
No, so it's only like when you run it locally that you can get this level of detail. And so we use it extensively for testing. But if you're building with Commonware, you're using this thing to get the same level of assurance. And so the idea is like you can run a virtual local P2P network, run a local whole system that you would deploy, and then it is run deterministically. And so that if it fails in any test run, you can immediately get back to that exact point.
So this is a very different testing like experience than say first testing, right? First testing is like you just hit and probabilistically you get something.
So you're going to love to hear that fuzz testing we've actually are almost now integrated into it. So you get both now. So you get the deterministic testing, and then it will use that seeded run to then now fuzz interesting paths from that deterministic run to reproduce. So the motivation here, very briefly, is when you're doing distributed systems development, oftentimes you'll hit a bug and be like, what the hell happened there? And like it takes like 5 days to try and reproduce it, even if you can. Half the time though, you're like, I hope that doesn't happen again. So the whole point with this is that if you can imagine that if we are encouraging people to like tune and tweak everything, testing becomes much more important to the application too. And if you don't take that into a first-party account, all Commonware will be known for is like a bunch of cool little gadgets that don't work very well because like you can't maintain them or you can't integrate them in a reasonable way. And so the deterministic runtime is there to make sure that if you mix and match all these things at different layers, that like you can keep it stable across updates, across like performance tuning, and that if you run into a bug, the time to debug it is much shorter. So the only reason why we're able to do all this consensus work to begin with is because we have like so many layers of these deterministic tests that if one thing fails, I mean, we immediately know how to reproduce it and then can debug it. So it's dramatically shortened, our time to develop.
This is like an open secret sauce, huh?
Yeah, we've written blogs about it. We do not think we could do what we do without this runtime, and that's why it was like basically the short track here was like, okay, when I started Commonware, I was like, I'm going to build a P2P. That seems to be like the obvious first thing that anyone needs, authenticated P2P. And I had that working, all using like Tokyo for people that are into Rust stuff. And I was like, cool, it works. I was like, how do I test it? And I was like, I guess I can just like kind of like run a local Tokyo cluster, and like if that passes, it's probably fine. And I was like, maybe we could do better, but at least it works. I'm one person, a small startup getting off the ground, have a bit of consensus. And then I started writing consensus, and I immediately was like, I have no idea if this is safe. I don't know how to test this. And then that's when I was like, fuck, I need to back up, like rethink and make sure I can actually do this reliably. And so it took a detour and then finished Simplex with all of the deterministic runtime in place. So now, everything, if you look in the code base, you'll see it is like this magical context we pass around everywhere. And that magical context is what allows us to run the same code in test and prod. And then in the test environment, run it deterministically to test and simulate. And then in prod, run it via like an actual efficient environment. So, and that production efficient environment is like IOU ring compatible, like it's fast, it's efficient. And so we think we've abstracted it in a way where there's not really any overhead of having that because of this. So that's very deep in the programming side, but that's
fantastic. So you have P2P, you have Simplex for a consensus.
So Simplex is where most people start. We have authenticated P2P, which is our own P2P stack that we built from scratch with like our own stream, own handshake. We use like all the way from scratch because it's authenticated and encrypted, and the authentication component is actually just your validator public key. So there is no like TLS certs, there's no like self-sign, whatever. Like it's just you just sign a message with your validator key, and then you form an encrypted channel, and that's it. And so this was another area where I saw a lot of complexity. And I think the other thing is that we're big believers for high throughput networks that authenticated P2P is the right way to go, which means that you know everyone you're talking to, and you're only connected to other participants in consensus. So it is not open P2P. It's only P2P of people that are in consensus. And then from that, we relay data out of consensus that people that are not part of consensus can use. Because the small thing there is, if you're trying to push the limit on consensus performance and like application performance, every like resource counts. And so if you're spending 30-40% of your CPU like serving random stuff to strangers on the internet, it immediately takes it out of your throughput that you can hit. And you don't need to do that. There are other mechanisms to like serve data to peers around the internet. And so the idea is that only validators are part of it. And so we wanted to have a P2P network and like topology that worked with that idea.
Okay, the one important thing here is serving data. So is that a separate mechanism in itself? Suppose I'm not part of consensus, but I want to just retrieve data, say data availability. That's the problem.
So I mean, it's up to the applications to decide how they want to like get data from consensus out to the world. So that's the business of Commonware, is we have like infrastructure that helps with that, but like it's not enshrined in the Commonware library. You can do whatever you want to. Like imagine like you're building like some EVM thing on top of Commonware. Like there are tons of infrastructure providers today, and all you would do is just like pass the data to one of them, and they could serve the data the same way they would today with any other EVM chain. But yeah, the idea is that this is one particular type of P2P. So like the way that the Commonware library is architected is that if you wanted, let's say, a different type of P2P, don't use ours, and then just use our consensus. And so you can pull and mix and match. There's no forking. You just, instead of importing our P2P, you just import your own P2P, and that's the only change. So that's how you should think about like it just feels like programming. I guess it's not meant to be like some sort of like all-knowing framework for you. Yeah. So that's it. And then the third big one, I'll stop there, is our cryptography, which is we have like a threshold BLS implementation that's pretty efficient.
So that BLS implementations, I was just curious about this. I saw some performance benchmark somewhere you guys have mentioned. So what was different that you guys did as compared to cryptography? Because people have been working on making efficient cryptography for a while.
Yeah, so we don't today like really do a lot of rolling our own cryptography. So like especially on the BLS side, we use Blast, which is great. The problem is that Blast is very low level. So if you've used Blast, you know this, and they try to like wrap it with some really great functions, like in bindings in different languages. But it still leaves a lot of like knobs to tune that you really shouldn't tune. And so we wrap it in what we think is a pretty like a type safe interface, like tries to prevent you from doing things that you can't do. So like we have a great threshold DKG system where like it just kind of handles all of those open questions for you, and you just think about partial signatures, combine the partial signatures into a threshold signature, verify batches of threshold signatures. Like you don't really think about anymore like the low level ops. The things we've optimized for are we inject our own parallelism into the concurrent operations, and then we have our own math library, which I guess you know you're really into it deep when you have your own math library. But
Yeah.
that would be Lucas, who has been working on that. So we implemented like Zoda, for example, which is like this erasure coding scheme, and then to do that we had to implement a bunch of our own math to work with it because it has like unique fields that it wants to use. And so as part of that, we ended up optimizing a bunch of stuff related to math operations, and then those math operations are part of the threshold library. I think what you should understand about how we think about it is with Commonware, we're not trying to claim that we can do anything better than like a great engineer could. Like, could you come to the same conclusions if you looked at our code, looked at what's out there, and built something? For sure. I don't see why not. Our claim is that you probably don't want to. One, in that we don't think you'll do much better. Like maybe you do a little bit better, but like we think what we have is pretty close to the efficient frontier, and you'll save a ton of time, and you won't have to maintain it. So like we audit things, we test things, anything that we use, we like try to really make sure is solid. And so the pitch we have is like, well, if you want to get off the ground, and you know crypto moves fast, so like you want to retain the ability to pivot and minimize how much code you're maintaining to really just the set that is related to your application, you probably should just use a bunch of like off-the-shelf things for the things that you're not tweaking. Like you could build it yourself if you wanted to, but again, if what we've done is reasonable, it may save you like a significant amount of time to be able to do that. I think that's a harder pitch to make if it's like integrate this framework, because you can't really rip it out once you've started. Whereas with Commonware, like you can kind of pull pieces in and out if you don't like them. But with the framework, it's like you're basically ceding control over everything underneath, like some sort of execution.
So I'm guessing that was the issue with, say, Cosmos Chain framework or Subnets framework, because they all give everything. The whole package comes all together. You can't.
I think it's just it's for different developers. Like you could launch Cosmos Chain probably 3 months faster than you could a Commonware chain, and like with a lot less tweaking. But the question is like, then what? And like, if you did want to tweak it, how deep could you tweak it without forking the code? So like, we think of developers in like very different classes. There's the people that are just like, I want to deploy on an EVM. Then there's the people that are like, I want to run my own chain, but still EVM. So like go into an L2 world. Then there's like, I want my own execution environment, but like not really my own execution environment. I just want a few of my own transaction types. And then there's I gotta get rid of all of this. Like if I'm gonna actually do something crazy here, like I need to be much more vertically integrated into the stack. That's where Commonware is. So like we're not trying to say like any of those other things are like a waste of time or a bad idea. In fact, for like different developers, they're a great fit. Like if you want like what Solana's doing with like a single high throughput execution environment that like tries to like pool a bunch of assets on it for like different sort of financial interactions, like interesting. Like for sure, if you're a developer that's just worried about that, like definitely the liquidity is there. Go there and work on it. But if you're trying to build something ambitious that like let's say like has special ways that data comes in and out of the network, or like how transactions are processed, we think that the way Commonware is architected is really natural for doing that without having to rebuild it all from scratch. Or like as you build, over time replace the Commonware pieces that are things from scratch without delaying your launch for like 3 years. But yeah, I mean, it would be, I know Brendan has a lot of firsthand experience when he was at DYDX of like having a contract and then going into the L2 world and then, standalone network. So, I mean, maybe he can offer some perspective on what that, kind of journey's like. When he reached out and was like, hey, I think I might be a good fit for Commonware, I was like, I think that's an understatement. But yeah, go ahead.
Okay, Brendan, yeah, go ahead.
Yeah, no, I think just echoing the things Patrick said, basically, around the reason why we went with Cosmos in the first place is that, yeah, everything was already built for you. It had a proven track record of people building on it, and people just said, yeah, you can get up and running super quickly on this. Just because, making an MVP, getting something that you can actually test in the real world, testnet, mainnet, and sort of build on there, it's like one of the best things that you can build on with like, you can make your application custom in whatever way you want, basically. But definitely once you get to mainnet and you have your application and you want to start doing things that are not quite supported by the framework that you're in, and you start trying to push the boundaries there, then you go, okay, like how hard could this be? And then you end up either breaking a bunch of stuff or using it in a way that it's not intended to be used in. And so, yeah, the two things are sort of just the difficulty of pushing past that boundary of the framework, and then secondarily, like maintaining a fork of it that you're sort of like, is this worth pushing upstream? Are other people going to find this helpful, or is it like just one custom component for us, right? Like you might say, oh, we want some logic to run intra-block, like between every block, basically, but not every chain is going to want that. So yeah, basically just echoing the things Patrick said, but it's sort of like it's great up until a point, and then stuff gets really hard to work within that framework.
It seems like the summary here is that for the frameworks, your initial cost that you have to give is low as compared to Commonware, but as the maintenance, as you go forward in time, you have to do tweaking, you have to do maintenance, the plumbing cost just goes up and up in the frameworks. But in Commonware, it already comes with the knobs that you can just switch, you can turn around, and the cost is much lower. But
we think it's a better long-term fit, but it's not a great fit if you're trying to get something up today, which is where we think is like the interesting applications come out of anyway. So we're very okay with that. But yeah, I mean, it's not for everybody. I think a lot of startups or new companies, like they try to be everyone, like something for everybody. And I think that's like the whole pitch of a framework, right? It's like every application could use this. And our pitch is, or like the way I think about it is, if we're everything for everyone, we've gone the wrong direction. Like we definitely want to be focused, I think, on people that have a pretty solid understanding of how these things work, and now they want to like really push the envelope on or kind of push the frontier forward around what we can do on chain. And that's the people we think are most exciting to talk to, and those are the people that we think are going to drive most value in crypto over the next decade. And so that's really the focus for why Commonware is organized the way it is as well.
I see. So talking about the applications, like dictating what kind of primitive they want to use. Tempo, it seems like they are using a specific instance of simplex called Minimit.
So right now,
how did it came out?
Yeah, so right now they're using Simplex, and so you can look at the repo for that. Minimit is the next evolution of our consensus work that we came up with and are working now, or very shortly we'll start building out. But yeah, the idea there, and I have to give full credit to like the Solana folks, particularly Roger. I was at the Solana Accelerate event in New York last year. They invited me to speak around some like multi-concurrent proposer kind of style stuff we've been working on as well. And I didn't notice at the time, but like basically they had scheduled this like big keynote or big reveal for Solana stuff. And they were like, yeah, we have a proposal to change consensus. That's Alpenglow. And unlike everybody else, we're taking a very different perspective on crash tolerance, like basically fault tolerance. So instead of 33%, which seemed like the golden rule, you could never like push against, and in which case simplex I think is optimal for, provably optimal for. They were like, nah, we're good with 20% Byzantine fault tolerance, and I don't know. I just had this mental block in my head the whole time, which was like, we can't go past 33% fault tolerance, like 20%. Wait, what? And everyone was like, you can do. And if you're familiar with the literature, there are a few big and important numbers that matter. So like the 33%, there's like a lot of, you basically requires this like 3-phase. And then if you go down to 20%, only requires 2-phase. So like being below 20% doesn't really buy anything because it's already still 2-phase. And then being, below 33% doesn't really buy anything because that's kind of the limit for 3-phase. So that 2-phase is crazy. And so for people that, it sounds like your listeners already kind of went over this a little bit, but it's kind of deceptive. I almost think of it as 2-phase and 1-phase, but it's 3-phase because there's a proposal broadcast in there. So in simplex, you have the proposal, then you have the voting, then you have the finalization. The trick you can do with a 20% Byzantine model is you can just have a one shot. If you get 80% of people that vote, it's finalized. That's it. Crazy that works. So a huge step in like terms of like what the practical performance is, because you're sending literally half the messages. And the speed of the view can be much faster because, again, it's only one round of voting. It's 80% instead of 66% or 67%. So like depending on how the distribution of the network looks, 2 rounds of 66% may be faster than 1 round of 80. That's something that Alpenglow and Kudzu have focused on. But yeah, it's a huge change in what you can do. And so like I was at this talk and I was like, shoot, like you imagine like you're a small startup and you're like, we're working on like what we think is like the best consensus for this 3-phase. And like, if people are cool with 2-phase, like why would they use this? And so at that point I was like, well, we looked around at what was out there. Brendan and I did. I remember I came back and we were talking about it. And we were both like looking at all the mechanisms that were out there. And it just none of them spoke to us in the same way, I guess, that simplex did. Like they're very complicated. If you look around, they do a lot to like, a lot of them focus on this notion where we want this crash fault tolerance fallback slow path so this was the whole thing with Alpenglow is they call it 20 plus 20. So it's 20% Byzantine, 20% crash fault. And so for different applications, that could be great, right? Because like you can now tolerate also like in practice, some would say that's even better than the 33% fault tolerance because it's like most of the time you're dealing with crash faults anyways, and the idea that now it's like even a bigger tolerance to that is great. But all of them focused on this like crash fallback route. So like to do that, you have to organize the quorums in a certain way so that you can support this like fallback voting step and still be safe. And a lot of them will actually race. So they try to do the fast path, this like one shot 80, and this fallback slow path 2 round of voting thing at the same time. And then whatever finishes first is the finalization result. And then basically with very nuanced rules, they ensure that those things never conflict. So if both steps finalize, you know that they're always for the same result. So robustness, I would say, is the term that matters.
So this is like a safety protection. That's what they're trying to ensure with this one.
It's a different tolerance for like how faults are handled. Yes, exactly. And so the idea is that we'd rather save our like quorum allowance for this fallback thing to keep going rather than use it for something else. And so when I was looking at it though, and looking at the mechanisms, basically, something occurred to us, and full credit here to Brendan for like I think like some of the real core insight behind Minimit of like pulling it together, because I had some ideas, but admittedly like they were not nearly as useful as what ideas Brendan ended up coming with. And it was funny, like we basically worked on our own a little bit for like a few weeks, kind of proposing things back and forth, and then I was like, we got to get something out because like we need some sort of like 2-phase option out there that is like open and like just unrelated to any like kind of like network. Because I think at least in the space, if you like just implement what another network has done, it turns into this culture war on crypto Twitter. So we were trying to offer an option that was not associated with anything, because simplex came out of just research. It wasn't associated with it. It was funded a little bit, I think, by Algorand, but pretty open. And so we were like working on this on the last mile. And then I remember it so vividly, Brendan was like, well, what if we just like did this instead? And maybe Brendan, you can better recount that moment, because that to me was the most important one. Yeah.
Yeah, I don't remember exactly what it was about. I think we were it was perhaps some sort of fallback on the timeout mechanism or something. But yeah, I think sort of the main two ideas that were kind of married were the simplicity of simplex with like the very few message types, which is basically just vote for this block or vote to skip it. And then the work that Alpenglow and Kudzu had been doing on the assuming less than 20% Byzantine nodes. And I think also, maybe the third perspective is that was brought by Patrick and I was sort of maybe more the engineer's perspective, where we had implemented simplex and also messed around with other consensus mechanisms in the past as the ones actually coding it. And I think really prioritizing that simplicity and lack of code paths is really important, just because something on paper can be twice as complex, but it's exponentially harder to code, because you might have if something can be in the state A or B and the other thing can be in the state C or D, you can see how kind of flowing through those states, or the number of states that you need to track, is like an exponential. Like if you have 8 binary things, so 0 or 1, there's an exponential of like tests you need to write, things you need to keep in your head as you're doing it. And if you ever want to like either extend the mechanism or you want to change some of the code, then you need to be keeping all those exponential number of states in your head. And so really, I think the thing Patrick was talking about earlier, that none of the existing stuff was like speaking to us, was just like, okay, we can see how this works on paper, but when you are like, okay, I'm actually the one who has to write the code for this, like this doesn't seem like that fun of an exercise. So I guess that was like the third piece that maybe we brought, is like, okay, what is the thing we actually want to like write code for, basically? Because these things are deceptively, they seem like, well, they don't seem easy, but it's actually, once you start writing the code, there's all these little wrinkles that actually make it even harder than what you thought. So,
but the part that ended up being like the twist that ended up, I think, making Minimit interesting to so many people was, instead of thinking about this crash fault case, we were like, okay, if we simplified it a bunch, and this is where the kind of it emerged out of that conversation, was to say, well, if we remove this crash fault part, like in this fallback case, what can we do differently? And it turned out, like, the math worked out that to change views, or like kind of produce this notarization certificate without interfering with safety, you needed only 40% basically of the votes. So
so previously with crash fault you need 60%. Without crash fault, it comes down to 40%. So you can do even faster.
So it's a little bit nuanced, a little bit more nuanced to how you would say that, basically. So if we look at Alpenglow, there's these 2 paths that are running. And we're evaluating things in the case where like view change is based on having some certificate that indicates you can move forward safely, basically. And so in the Alpenglow case, on the fast path, you can change views if you get the 80% finality case, or you get, I believe, the first round of 60. Same thing works with Kudzu in the slow path. So what that means is like you can do this optimistic view change thing where like you change before it's finalized, and then you finalize the second round while you're in the next round. But it's not safe to exit that round of consensus until one of those 2 events has happened. Okay. Minimit, because of the trade-off of not having this slow path, that threshold for us is only 40%. So look at that and be like, okay, well, that's going to be faster because you have to collect less votes. But at the same time, also really interesting, you only need 40% of the network online to actually notarize votes, like produce notarizations. which is very interesting for some networks that want to like continue to like make progress when there are like significant outages.
Correct me if I'm wrong in this part. So is Minimit's goal is to make the progress? Like 40% is there, let's just go burr.
What I came to was to say, anyone I talk to, like, sure, like, safety, obviously, incredibly important. But if you ask them, like, do you want faster views and faster blocks? Or do you want this, like, crash fallback thing? Like, they want to go, you always want to go faster. Like, and until you're optimally fast, like, you're going to want to go faster. And so I was like, we have an opportunity with Minimit to basically claim that optimal bound. I don't know if we haven't proved optimality, but like pretty close to what we think is optimal on like the speed at which consensus can, like a responsive consensus mechanism can change views. And we think that's a very interesting corner to be in because we think that's where any application actually wants to go, is like, if you're dealing with crash faults, like, you know, I think most people are okay if you go from 33 to 20. I think Alpenglow was like, well, let's do 40 because that's better than the 33 in practice. But if you just say, well, if we're going to go to this 20% Byzantine, let's do 20% Byzantine and use the space to do more stuff on like the view change side. And that's where the real insight came from, was let's go as fast as possible. People just want to go fast, so let's give them the fastest we think you can do in this sort of security topology. And that's
Changing the gears, moving to the benchmarking and optimizations.
Yep.
So are you guys like using all the toolings, the primitives that you guys have built from Commonware for this Minimit implementation also?
Yeah, we are a huge like kind of like eat your own stuff. So like we build only everything that we do with ourselves. So like we don't we force ourselves to have all the mechanisms required to complete build outs of different experiences. So with Minimit, like we'll use our authenticated P2P stuff. We'll use like probably our multi-signature cryptography, maybe the threshold stuff, depending on how we do it. And yeah, we'll use that with our storage, like kind of journals to build it out. And yeah, we'll use the runtime that we talked about for ensuring that it's safe and that we can debug it. And then yeah, we have a bunch of primitives that actually sit on top of consensus that make it easier for applications to kind of process a stream that comes out of consensus, which may be lossy, which may have like holes in it. And so Minimit will just plug into that. So like you'll be able to basically just change your import more or less and go between Minimit and Simplex.
Yeah. How are you managing the throughput? Because if it's going so fast, there'll be so much data. Like isn't at certain point throughput becomes the bottleneck? Like some kind of trade-off comes, latency, throughput, bottleneck.
Yeah, so there's a whole other dimension here, which is like how you actually get the block data around the network, which we are spending a lot of time on like erasure-coded broadcasts, and we'll have like an example out hopefully the next month or two that takes advantage of like erasure-coded broadcast on Simplex at least. But on the Minimit side, same thing applies, which, I mean, you guys I know have done with a lot of the like EigenDA optimization stuff. Like number keeps going up, like where does this data go, or like how is it stored, right? So like people talk all the time about like 100,000 TPS, right? And even with like 200 byte transactions, like that's like 1.7 terabytes of data coming out per day. So like you want to run fast consensus, like I hope you have the money for it, because like yeah, it gets really expensive. And so the idea
is that where Tempo, like people like examples, like customer examples, like Tempo comes into the picture, like because they are servicing a lot of stable coin payments, right?
Our role as Commonware, the company, is to make that a tenable proposition. So like how can we make it practical to actually run at that throughput? So the first thing is like all the Commonware library stuff you see, which is open and you can hook up, and it's like what we think is like pretty efficient for the hardware it's running on. But the second part is like how you actually make that accessible to people to use, because like if the chain just runs and no one can interact with it, like it's kind of the whole point, right? And so that's where like Commonware the business lives, which is like we're building a bunch of proprietary infrastructure that sits next to Commonware to offer an option that we think is very affordable or hope to be for people that are running at that kind of throughput that you can't really do with infrastructure that's available off the shelf today from like the big cloud providers. So think of it as Commonware, if you use it a certain way, lets you really push the throughput. That can be a function of just what your application is or just faster blocks. As soon as that becomes where you're at, you will run into a huge problem, which you can solve yourself or we can solve together, which is like, how do you actually deal with that much data? And so we think about this life cycle of an application, which is like you start from wanting to go fast, you actually get fast, and then you're like, wow, this is a lot of data, and I want to serve it to people at low latency. This is a whole other build out of equal or more sophistication than what I did on the network, but a totally different type of building. And so for all these teams that are very like protocol minded, it's not necessarily an easy jump to be like, okay, well now we got to build these like Kubernetes clusters that like do this interesting like object storage. Like it's just a totally different type of thing. And so our belief and hope is that teams build on the Commonware side, they launch all this cool stuff and applications, and then with the Commonware infrastructure stuff, which we call ExoWare, you don't have to build your whole own DevOps team to manage it. And that's the hope of like kind of what the business of Commonware is.
Oh, yeah. So is ExoWare like so when you say infrastructure, is it like a Kubernetes that already all the setup is there and I can just use it? How to
it's just like Commonware. It's a little nuanced. So I got to work. We haven't unveiled it much publicly because we're still working on the pitch, right? But we don't ever want to run your validators under no circumstances, or we don't want to store your keys. Like if that was the case, just use AWS. Like then this all is for nothing, right? So we don't do that. We do everything that's around it though. So you have data coming out of the chain and you want to use the chain. There's a gap there, a chasm that's only bigger if you're at high throughput. We are interested in solving those problems for you. So like how does block data become queryable at low latency? How do we stream that to your browser? How do we do that safely? So like for example, our Alto demo has like a browser-like client that verifies consensus certificates that allows you to process data. And then at the same time, you're now submitting transactions. How does that get to validators? So those are like the edges. And then within the actual validator network, let's say that you have 10, 20, 30, 50, 100 megabyte blocks. How do you get that around the network efficiently without blowing up the validators? Because if the cost of validators is so high, it could be, very difficult to actually get off the ground. And so what if we offer like different like sort of relays and broadcasts that basically take the burden off the validators to push all that data around, but doesn't actually change the safety implications because they still have all their keys. So like where are the like in the same way like places where we can add plugins at all sorts of parts of the stack with infrastructure to drive throughput up and drive costs down. All optional. So like none of this is required if you're using Commonware stuff. But we think ultimately as you move up the throughput curve, you need to be thinking about infrastructure at every step if you want to do that at any sort of reasonable cost and like reasonable throughput. So as you move up the throughput curve, you can't really think about like blockchain scaling and infrastructure differently. Yeah.
If I have to summarize this in one line, this is a kind of an API service for reading and writing from a high scale, high throughput, low latency blockchain to like off-chain service modules like browser, for example.
So like you could, for example, on this infrastructure, you could build an explorer, you could build wallets, you could you could ingest it into your own backend. It's very low level. It's not like the same sort of thing where like we're running RPCs. That's not what this is. This is like how are we getting block data out? How are we transforming block data into like different data that you can then query? It's much lower level, just like the.
It's a synthesizer kind of a thing.
I would almost call it like just a really sophisticated relay. Like how do we get data from consensus to all the people that are interested, and in a format that they are happy with.
And it's already there. Like people can just use it already. Not yet.
So ExoWare is so you can imagine like an order of events with Commonware, which is like, is Commonware stable enough to use in production? which very close, that'll be true. Once that's the case, we now have something that we can actually run in production. Like, well, it'd be great if that infrastructure existed. And so prior to that point, though, it's tough to build what we want to build because everything was still pretty like changing quite a bit, right? So you can't really know like maybe what the exact like shape of the data is going in and out. So we want it where it's a staged build out, really. So when I tell people about Commonware, I'm like, this is a multi-year like long-term thing. It's not like, oh, like we're trying to get our product to market in 2 months. This is like actually there's an initial product which is free and doesn't make any money, Commonware library, and we want to keep it as awesome and free and open as possible. And then if that's good, then the actual business can be built, which is so like getting that through to our investors and customers and everything.
This seems to be like a Databricks model where they launched the Apache Hadoop and all this thing, and then the Databricks they build the whole thing on top of it.
I think the really important thing I want to call out is like I think a lot of the open SaaS models, like they'll nerf the open version, so like you really need the SaaS thing to actually use it. That's not the idea with Commonware. Like Commonware on its own is standalone and does whatever it does. What we're doing with the infrastructure side is purely augmenting. So like, oh, you want to store all of this in a database that you can query. Like clearly you can't do that with a validator. So like it has to be somewhere and someone has to build it. We're not trying to basically say, oh, no, we can run your validators better than you, so run it on. That's not what we're trying to do. What we're trying to do instead is say like, you need these capabilities that sit next to your chain. You can build them from scratch, but we just want to warn you, it's not easy. Like it's hard, and it's multi-cloud. It's like a lot of super scalar like sort of thinking around architecture. It's a huge build out if you just do it for one chain. So you can do it. Like it'll work all the same if you pull it. Like some applications, like they're huge infrastructure people. Like they love that, and for that we're like great. I mean, then let us know if anything breaks in Commonware, and we'll try to fix it. But otherwise, like have fun, right? And then there's other people that are like, I tried, and you're right. I can't just put every transaction into DynamoDB. What should we do? And we're like, we have some ideas. So that's where that business sits. So
what are some next set of primitives? Like, are you guys planning for the Commonware?
Yeah, so the first one is definitely Minimit, which will come shortly. Well, not shortly. It'll come next. The other one that we're really interested in is like some more advanced cryptography throughout the stack. So we already have threshold stuff, but we use like a synchronous threshold DKG reshare. We'd like to make that an asynchronous. So like kind of there's a new paper out from like 3 months ago called Golden, which is really interesting from some really awesome researchers that we think is a really good fit for what we're trying to do. So Lucas will probably get a start on that soon. And then we are working in the threshold encryption, decryption world. So like how can we encrypt data before it's in consensus and then decrypt it on the fly? So we already have like time lock encryption, but this is like on-demand encryption and decryption, which is a whole other thing. So that's been fun. But the stuff that's more tangible is that we'll finally hopefully launch our like kind of state database stuff in prod in the next month or two. And that will be where at that point you can now build a Commonware chain from scratch just with Commonware components from start to finish and run it in prod. And so right now, if you have your own execution environment with your own state, that's totally possible today. But we think it gets really interesting when we have this like super optimized database that then fits into the whole thing. And so we're going to work on an example to showcase that shortly once that's put together. But so in summary, the Minimit stuff, some new stuff on the cryptography side. And then our plan for the next quarter is really just to optimize it. Like now that we feel really good about the code and what it does, now it's like, let's make it way faster because we're aware of a number of opportunities to reduce, resource usage.
You guys are really making blockchain go faster and faster and faster.
Yeah. Trying to do it and then make it so it's just a commoditized thing. So like anyone can use it however they want to, and then we can compete. Applications can compete on the application rather than trying to like have an ownership over like what we think are just like should just be open code. Yeah.
Do you guys also work with some of the bigger foundations like Ethereum Foundation, Solana Foundation on improving they have their own architectures and all these things. So do you guys work with them also?
So we don't talk about anyone we work with until those people talk about working with us. That's our policy. But we, fortunately, a lot of the people at Commonware have been in the space, for years. So all of us have like pre-existing relationships with a bunch of great engineers, and our door's always open if people, want to chat about stuff. In fact, we're just about to kick off our search for like our next big Keystone partner. So if people are interested in that, listen to this, you know where to find us. But I think the thing that comes up a lot of times is like with Commonware right now, it's definitely better suited if you're building from scratch, like kind of like a greenfield thing rather than trying to augment some existing network. So, and we also know like from our own experience as a team, like migrations, very hard to build a startup around. Like if to get off the ground we required Ethereum to migrate to Commonware, like okay, well, like we're not going to get off the ground, right? So we have not focused much on like existing chains, although many have reached out to us and some are planning to use it. Our focus we spend more time with people that are building things from scratch because it's just easier to hook Commonware up to that. Yeah.
Awesome. So today's big idea is that the performance doesn't come from like clever tricks inside a framework. It comes from choosing probably the right primitives and being honest about the trade-offs you are making. So we started with Commonware's philosophy of specialization, then talked about the Minimit as one concrete way those primitives come together.
Yep.
So Patrick, Brendan, thank you for walking us through both the philosophy and the engineering and the future that you guys are thinking about. It was really great to hear about that. I'm sure many people have like almost similar questions, and they will find it really clarifying to hear all this discussion.
Yeah, I mean, the great line of questions. I think, like I said, I have not successfully explained Commonware in less than 30 minutes. So hopefully people get to this point and listen to the whole story to get the real sense of it. But I mean, yeah, we've been fortunate enough to have some people though make it all the way through the 30-minute explanation, and that they do understand what we're trying to do and have been, awesome supporters of that. So thank you for inviting us on to talk about what we're doing. And if the Commonware stuff can be useful to people building stuff, it's MIT Apache 2. Feel free to grab whatever you want. And if you run into any issues, open up an issue and hopefully we can help.
Awesome. Thanks for listening, and we'll see you in the next episode.
Thank you.